is our first day of new notes, and this is bonding that we're going to be talking about. But up here we have written polyatomic ions. So what I would do is at the bottom of your paper, you've got some room down there at the bottom of your paper, write the word polyatomic ions and this definition. Polyatomic ions are, if it's poly, it's more than one atom, because it's polyatomic, more than one atom, and if it's an ion, then that means it has a charge. So more than one atom with a charge. So I just want to show you this right up front because we're going to see some examples that involve them once we get started. They are bonded together. And the other thing to note about this is not only are they bonded together, but we're going to see that they're bonded with things like oxygens, sulfurs, hydrogens, nitrogens. So all of those are what type of atoms? So nonmetals. So that means that it's going to be covalent bonds. Okay, so a little reminder about what we have learned so far. We've talked about electronegativities, and we can see that we also remember that the difference in electronegativities give us some insight as to what type of bonding is occurring. So if you've got a really big difference, then that's going to be an ionic bond. If it's not quite as big, it's going to be covalent, but it's going to be a polar covalent. And if it's a really small difference, that means those atoms are getting equal share of those electrons, so it's going to be considered nonpolar covalent. So what you should see from this is that the type of the bond really depends on how strongly that bonded atom attracts the electrons. So we're looking at how well it attracts it. Going back to something like ionic, if we look at it's a big difference in your electronegativities. So in that case, you would expect that to be something with a large electronegativity bonding with something with a small electronegativity, which makes sense. Metals and nonmetals. That's what you see bonding with ionic compounds. So that's why those numbers work out that way. Okay, so our first example that we have is ionic bonds, and we just really mentioned that this is going to be a bond between a metal and a nonmetal. And this is formed when atoms, what are those atoms doing with electrons? They can lose them, they can gain them, so they're transferring. So they transfer electrons. So in the process of transferring them, the metals, those lose the electrons, getting a positive charge. Nonmetals gain the electrons, getting a negative charge. So you've got that difference in charge that creates that electrostatic attraction, and that's what causes them to stick together. And it's a really strong bond. It's a strong attraction. So here we have an example of some sodium ions and chloride ions. And notice that it's a nice structured pattern that we see here that's formed from that. And then some properties that we'll see with ionic compounds. Because it's so structured in such a strong bond, you expect to see really high melting points. So if you were to try and take sodium chloride, let's use that as our example. Sodium chloride. If you took that, put it into a frying pan and went to your stovetop and tried to melt it, you're not going to be able to do it because it takes a really, really high temperature to reach that melting point or the boiling point. Also has a low volatility. So as far as volatility goes, that means the ability to break into a gas. So if it's a low volatility, then that means it doesn't have much of an odor. So we'll say low odor. So you don't really smell sodium chloride too much. It doesn't have a strong odor. Conducts electricity. Well, it does, not in the solid form, but if you were able to melt it, get it into that molten form, then yeah, sodium chloride would conduct electricity. Or if you took sodium chloride and threw it in water and got it to dissolve, then it's considered an aqueous solution, and it would be a great conductor of electricity. So this is the big thing. Remember these differences, is that it will conduct electricity, but only in the aqueous or molten state. Aqueous is dissolved in water. Which takes us to the next thing, that most of them do dissolve in water. And again, if you think about the common example that you guys know, sodium chloride, then that might be easier to remember it, that sodium chloride does dissolve in water really well. And then, again, overall, we're talking about real strong, rigid crystalline structures. So we would expect a lot of ionic compounds to exist as solids at room temperature. Then we get to covalent bonds. We're not talking about metals and nonmetals. Instead, we're talking about two nonmetals. And actually, it doesn't have to be two. It could be three. It could be, but you've got a bond between nonmetals. And this is going to be formed when atoms, remember, what do nonmetals do with their electrons? They gain those electrons. So he wants them. No, he wants them. No, he wants them. This is like kindergarten, right? So what they have to do is they have to share electrons. And here we see that the electronegativity difference is not going to be quite as great. It's going to be less than 1.67. And by sharing these electrons, and now they feel like they have a full outer shell, so they'll be able to share them to where they get a full outer energy level just by sharing, so they'll have some in common. Let me just go back real quick. Here we see in these carbon atoms, we see that this is going to be a covalent bond that exists, but this carbon doesn't have a greater share than this carbon, so that would be considered a nonpolar covalent molecule. Whereas if you were to look at electronegativity values, which one do you think is greater, oxygen or hydrogen? Oxygen's a lot greater, so you could even look on your periodic table and see that oxygen has a much greater electronegativity. He is the electron hog, so there's a lot greater area of electron density around that oxygen than there is around the hydrogen, meaning that's polar covalent. It's unequal sharing. Okay, so now we can look at properties of covalent compounds, and as opposed to having high melting points, these guys are going to be much lower. For examples here, maybe think about, I like the example of Crisco, or gasoline, or even the gasoline that comes out of the jets back there, methane gas. In this case, we are looking at things that have a really low melting point. You can hold Crisco in your hand and it's just going to melt right away. Or you can think about methane that's back there in the gas jets. Well, even at this temperature, it was a chilly morning this morning, it's still above its boiling point. It's existing as a gas. So has a very low boiling point, low melting point. High volatility, you can smell it pretty well, so it has an odor to it. Does not conduct electricity, not a good conductor. Here it says most do not dissolve in water. That's true, but some do. I just don't want you to get stuck on that because it's very possible for some of them to dissolve in water as well. And then typically you're not talking about a real hard structure because it's not near as strong of a bond. Instead you'll have softer non-crystalline structures. Oftentimes they'll exist as solids, liquids, or gases. It could be any of those. All right, so now we can look at our last one, which is metallic bonds, and we really haven't said anything about these, and the reason is they have nothing to do with electronegativity differences. So metallic bonds, here it says an atom achieves a more stable configuration by sharing the electrons in its outer energy levels, so I'm going to just say it's valence shell, with many other atoms. And a bond between, this is a bond that occurs between metals. Now before I go further with this, I don't want you to think that I can take two metals and have them bond together. If I take metals, they do not bond. Instead, they're mixtures. For example, you don't see brass or bronze up there on the periodic table. Instead, that's a mixture known as an alloy of some different metals. So they do not bond. But if you were to take a metal, let's pretend this is iron, or maybe it's gold, something like that. What happens is metals give up electrons. So they give them up, and therefore by giving up those electrons they have a more positive charge to them, and you get all of these extra electrons that are just floating around outside. These electrons that are floating around outside are attracted to the positive ions of those metals because they gave up those electrons. So it kind of holds it all together. And the best way to describe this is a sea of electrons. And we have this little video that will show it in this next one. Say that again. Exactly. The electrons do not belong to any one atom. They just share with all of them. So there is a little video that we're going to watch that shows that. Okay, so you guys at home missed out on that video, but just went through showing about the sea of electrons. So what we can say about metallic bonds and the properties, they have a high luster, which just means that they're shiny. They're malleable. They can be hammered into sheets. They're ductile. They can be pulled into wires. They conduct electricity really well. That's why we have wiring in our house, copper wiring in our house. They don't dissolve in water, which you guys know that already. And in order to get them to melt, we have to increase those temperatures really, really high. So high melting points. And then, now that we know something about ionic, covalent, and metallic bonds, what we can do is we can illustrate these with diagrams. And this first one is showing electron transfer. These are the ones that people hate, and these are the ones that people usually miss on the quiz or the test. Do not be that person. So electron transfer, if you're transferring electrons, sounds like it would have to be an ionic compound. In other words, we're going between a metal and a non-metal. So the way you illustrate these, and we're going to do two of these, they can get messy. We're showing arrows and what's going on with the electrons. But you just take your element, sodium, and how many valence electrons? 1. And we add it to chlorine. How many valence? 7. 1, 2, 3, 4, 5, 6, and 7. So then in order to show the transfer, you have to physically draw the arrow that's showing what's going on. So sodium gets rid of 1 electron. Chlorine wants to gain 1 electron. What a nice little pair they make. So then you show the result. There's 1 sodium atom. So we're just going to write sodium. But it's no longer a neutral atom. It has gotten rid of the electron that it had, its valence electron. So what's the charge now? +1. And notice, by getting rid of that electron, yeah, there's an outer shell underneath that that's full, but we do not illustrate that with any dots. So there should be 0 dots around that. And then in this example, we've got chlorine that has formed the chloride ion because it has 8 dots, 8 electrons, valence electrons. So what's its charge? -1. So every time that you draw one of these, your metal needs to have no dots on it, and your non-metal should have 8 dots on it. And then you throw the charge up there as a superscript. Okay. Yeah, and you show brackets with the charge. So we're going to do one more example, and then I'll talk about the ones that can get the toughest. Okay, so calcium, valence electrons, 2. Bromine, 7. Okay, so calcium happily gives bromine an electron. Uh-oh, what do we need to do? What do? We need to add what? Another bromine. We have to add another bromine. Because calcium still has an electron to give up. So bromine, remember, oops, sorry. Yeah, bromine and barium are completely different. There we go. So we added another bromine, and calcium wants to get rid of this electron. So we show the arrow. Now calcium has gotten rid of both of its valence electrons. Those 2 bromine atoms were able to accept it. So when we go through and show the final product, you're going to have 1 calcium. What's the charge going to be? +2. How many bromines are we going to have? 2. And each of those are going to have their 8 dots. And then what is the charge on this bromine? -1. You're going to write -1, and this is what's commonly missed. Write -1. You happen to have 2 of them. That's where your -2 comes from. But up here, you write -1. So that's electron transfer. They're not pretty. They're not fun. They can get messy if you've got something like a +2 - 3 or a +3, -2. Those would be the toughest ones because you have to add a lot until you get them neutral. But they're not that hard. It's just a matter of showing the diagrams. Now what we'll spend a lot more time on is showing how electrons can be shared. So somewhere, here we go. Sharing of electrons, so if there's sharing going on, that's going to be covalent compounds. And again, you would notice that by seeing a bunch of nonmetals. You wouldn't notice metals in these. It's going to be a bunch of nonmetals. And the way we're going to illustrate this is if you have 2 electrons between atoms, that's going to create a bond, and we illustrate that with a dash. So a dash is the bond, illustrates the bond. And then if it's not between atoms, you would just have those 2 electrons with 2 dots. So those are going to be considered a lone pair of electrons, and you show those with dots. But we will do plenty of examples. Okay, here is our formula that we're going to use. We just need to know what this information stands for. So the first one, N, this is how many electrons are needed. Every single element out there needs 8, except which one? Hydrogen. And there is a little bit more to the story than what we'll learn about that tomorrow, but right now we're saying that they all need 8, except hydrogen just needs 2. We know that. So for this, since we personify these atoms so much, you can almost think about this as being what the atom wants to be stable and happy. So do you need to even look at your periodic table for that? No, not at all. So you know this is going to be 8 for each of them. This one's a little tougher because you have to look at your periodic table for it unless you've, memorized all these valence electrons. It's the number of electrons that are available for bonding. So it's going to be those valence electrons. So that right there says valence. And I think things are getting hidden here. But underneath this, valence electrons. So what this means is we're just going to be able to subtract those, and that difference is going to be what's shared. As far as valence electrons, you guys should remember, this is just a little reminder about valence electrons. And then here are our rules, what we're going to do. I like to start with this one, where I draw my most symmetrical skeleton structure. Once I've done that, I go back and I determine the number of bonds that we just talked about with that formula, which will make more sense after we do a few of those. And then we just start connecting everything and making sure that everything satisfies the octet rule. If you are ever given the choice of choosing the central atom, usually it's pretty easy and straightforward. But if you're given the choice and you're not sure which one to choose, always choose what's least electronegative for your central atom. Okay, first example. Here we have carbon monoxide, and I guess on your paper you've got, just think about how many you've got. I'm just going to do little sections of each of these, so make yourself some space. So this is carbon monoxide. To draw my most symmetrical skeleton, there's really not many choices. I'm just going to do that. But I want to calculate my needed, available, and shared. So somewhere next to that, make sure you write this down. Needed, available, and shared. How many does this carbon need to feel like he's got a full outer shell? Total. 8. What about this oxygen? 8. So 16 are needed by both of these elements in order to feel like they have a full outer shell. Well, how many do they actually have available? How many does this carbon have? 4. What about the oxygen? 6. So 10 are available, but they need 16. They only have 10 available. So what are they going to have to do? Share the rest of them. So you subtract it. If they can share 6 electrons, then they'll be able to feel like they have a full octet. Remember, each bond is 2 electrons. So if we divide it by 2, that's going to mean that there are 3 bonds. So, not many choices here. We've only got 2 atoms. We've only got 2 atoms. So 1, 2, 3. We're illustrating bonds with dashes. If it's not bonded, we do that with dots, but this is connecting 2 atoms together. So there are our 3 bonds. Now, If I look at my carbon, does that carbon feel happy? Does he have feel like he has 8 electrons? No, not yet. All he feels are 2, 4, and 6. He feels all 6 of those. He needs 2 more to feel happy. So let's give him 2 more. What about this oxygen? What does he need? 2 more. So your last step should be to double check. And at home, I know you can't see me pointing to these, but 2, 4, 6, 8, 10. So I added it all up, 2, 4, 6, 8, 10, and it equals the available. So that should always be the case here. Also, another way that you can do this is if you subtract this. If you said 10 minus 6, you get 4. That tells you how many lone pairs, or actually lone electrons that you have in that case. Okay, so just had a question about, does it matter where the electrons are placed, these lone pairs? And the answer is, keep them together as pairs. So these 2 electrons, don't break them up, keep them as pairs because we're calling them lone pairs of electrons. And then make sure that you put them somewhere other than this side. Don't put it on that side because that side's bonded. You've got 3 other options, 3 other sides, so it doesn't really matter where you put them from there. Okay, next one. We're going to do 3 of these all at the same time for the most part. We've got nitrogen, oxygen, and bromine. And all of those guys, you should be thinking to yourself, I bring clay for our new house. Remember, what are those all called? Diatomics, 2 atoms. All of these are 2 atoms that are bonded together, and we can see what they look like when they're bonded together. So when we do needed, available, shared, easy, don't have to even look at a periodic table. How many are needed for nitrogen? Okay, so for both of them is 16. What about total for available? 10, 5 each. So they need 16, but they've only got 10 available. So it looks like they'll have to share 6, which means 3 bonds. This is very similar to what we just did. If we put 2 more electrons there, 2 more here, now nitrogen feels content, feels like he has a full outer shell, each one of those. So that one's just like what we just did. Let's do oxygen. Needed, available, and shared. Again, it's 16 for needed. How many are really available? 12. Well, looks like they're going to have to share 4 electrons. So what type of bond is that going to be? 2 bonds. So it's not a triple bond, it's a double bond. So those we're going to be using terms double, triple, single. And then what about this oxygen right here? What does he need to feel happy? 2 more lone pairs. Right, so 4 altogether. Same with this guy. We're going to do that last step of counting them up. 2, 4, 6, 8, 10, 12. We know we did it right. Or if you'd rather, you could say 12 minus 4 gives you 8. 2, 4, 6, 8. That's where those lone pair of electrons come from. So either way, you should be able to always do that last step of double checking and make sure that you have the right number there. Okay, last one with bromine. We have needed, available, and shared. So needed is 16, available is 14. So they will have to share 2 electrons, which means just one, a single bond. How many lone pairs, and think about how I term that, how many lone pairs does each bromine need? So that's how many electrons, how many lone pairs? 3. And then you do your last step of checking. 2, 4, 6, 8, 10, 12, 14 should always add up to your available. So, so now we have a quick example of just showing what those look like. And then finally, our last little bit that we have. We've got water, which we're going to make our most symmetrical skeleton, which we're just going to say, at this point, I'm just going to do this. For needed, available, shared, How many are needed? Think about this one. 12. Okay, so we've got 8, 2, and 2. So there's our 12. How many are available? 8. So don't forget about hydrogen. Hydrogen can't hold 8. He doesn't want 8. Well, okay, so the question was, is hydrogen less electronegative than oxygen? It doesn't even matter if it is or not, because hydrogen will never ever be a central element. And I assume you're asking because we talked at the very beginning, we talked about the least electronegative element goes in the center. So we're not really given, we know that hydrogen can't ever go in the center. You're going to find some, maybe even tonight's homework, I don't remember, where you have to think about the least electronegative. So this is not a situation where we have to think about it. Okay, so we see that 4 are going to be shared, so that means 2 bonds. You can probably see where the 2 bonds are going to go. And we put them right there. So, hydrogen, is he happy? He can only hold those 2 electrons, can't take any more, so he is happy. Same with this guy over here. What about the oxygen? Needs how many lone pairs? 2. So when we add it up, 2, 4, 6, 8, we did good. So it all adds up right. Okay, then we get to, what would we call something like this or this? It's what you just wrote down in front of your page. Polyatomic ion. So you have more than one atom bonded together with a charge. So in this case, let's do SO4 minus 2, happens to be known as the sulfate ion. So I'm going to choose S as my central atom, mainly because he's different than the other 4. But if I looked at my periodic table, it goes against the least electronegative thing. So in this case, you start by making your most symmetrical skeleton. If you have an option of just a singleton of a couple different things, where you have to figure out which one's going to be your central atom, then that's when you go to your least electronegative going in the center. So here's my most symmetrical skeleton, and I'm going to be thinking about a central atom. I'm not going to be making some funky chain of these things or doing rings of these or anything like that. I'm going to have a central atom. So when I go through and I think about my needed, available, and shared, needed, pretty straightforward. There's 5 of them, so it's what? 40? Okay, available gets a little tougher. Let's start with what we've got. If it was just SO4, how much does S need? I'm sorry, how much does it has available? 30. Good. Because S has 6 and oxygen has 6 as well, so there's 30. But it's not just SO4, it's SO4 with a -2 charge. So what is that -2? What do you think we do there? There's 2 more. So you add 2 more electrons, giving that difference of 8. So you're going to have 4 bonds. 1, 2, 3, 4. Again, you're bonding to a central atom. So let's look at the sulfur. Does he want any more? Nope. What about the oxygens? How many lone pairs? 3. And when you add them all up, you would sit there and count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yay, we did it right. And the last little step that we want to do for polyatomic ions, it's most correct, and I'm going to make sure, I will count off if you don't do this. It's most correct if you put it in brackets and then put the charge in the upper right-hand corner. So that's how you would write that, SO4 with a -2 charge. Okay, we have one more, and then we're done. Last one's a hydronium ion, H3O with a +1. So in this case, what goes in the center? Oxygen. Got to. There's no way hydrogens can do that. Doesn't really matter if you make these kind of at 90 degrees or 120. Doesn't really matter, but I'm going to make it like that. when I set it up as my needed, available, shared. Needed, how many? 6, 14. I'm going with 14 because you've got 2, 4, 6 for your hydrogens plus your 8 for your oxygens, give you 14. As far as what's available, think about this one. Okay, so we start with 9 minus 1, and we subtract it because it's a positive charge. So since it's a positive charge, that means you have 1 less electron. You got rid of a negative particle. So we had 6 for our oxygen, 1 for each of our hydrogens, and then we subtracted 1 more, and that gave us 8. So looks like they're going to have to share 6 electrons. They really need 14, but they've only got 8 available, so they have to share 6 electrons, which means 3 bonds. 1, 2, 3. Hydrogens, are they good? Yep. What about oxygen? Okay, so a lone pair goes on oxygen. When I add it up, 2, 4, 6, 8, all looks good, so we know we did it right. Throw it in brackets, and we are done.